Introduction: The Lie of Consensus. Hello everyone, and welcome back to Lecture 15 of our series on wave mechanics. Today, I want to pull back the curtain and share with you the actual, unedited history of how our wave mechanics theory was born, and how we overthrew the dominant, peer-reviewed consensus of microwave absorption. When we first challenged the mainstream theory, the reviewers of top-tier journals tried to silence us. They wrote, "These authors have no long history of researching microwave absorption. How dare they claim that the sacred formulas in our textbooks are wrong?" But today, I am going to show you that our extensive groundwork in transmission line theory and crystallographic synthesis is exactly why we were able to spot the errors that they had been blind to for 40 years. Stage 1: The Foundations of Crystallography and Chemistry. Let's look at the timeline. From 2010 to 2017, we weren't just thinking about microwave absorption, we were mastering the physical chemistry of materials. Barium hexagonal ferrites are notoriously difficult to synthesize. Traditional metallurgy calcinated hematite under high temperatures for days. We revolutionized this process. By understanding the close-packing model, we introduced divalent ferrous ions as reactants, heating them to guide the crystal growth through magnetite and magamite cubic intermediates. This cubic-to-hexagonal mechanism achieved near 100% purity and unmatched synthetic efficiency. While doing this, we deeply mastered classical transmission line mathematics. We published comprehensive papers in the Journal of Superconductivity and J. Motter Sci. We mastered their rules. And because we mastered their rules perfectly, we knew exactly when they were violating the laws of physics. Stage 2: The landmark 2018 discovery. In 2018, we published our turning point paper in AIP Advances. We proved a mathematical scandal in their literature. The mainstream formula claimed that reflection loss varies with sample thickness in a wave-like manner. This implies that as a wave travels deeper into a lossy material, it somehow gets unabsorbed and reflected back out of nowhere. We showed that this is a mathematical artifact of an incorrect formula. They were substituting the input impedance of a backed film circuit into a single interface reflection equation. In our equations 17 and 18, we restored mathematical sanity. We showed that wave reflection must be evaluated using the material's characteristic impedance, which is independent of thickness. Stage 3: The mathematical proofs of monotonicity. In 2019 and 2020, we published definitive papers in the Journal of Materials Science and Materials Chemistry and Physics. In Equation 2 of our 2019 paper and Equation 21 of our 2020 paper, we provided the ironclad mathematical proof: at any fixed frequency, true material reflection loss is a monotonically decreasing function of sample thickness. Period. The thicker the sample, the more it absorbs. There are no magical peaks for a bulk material. The peaks are a property of backed films, not the material. Conclusion: The birth of wave mechanics. In 2021, we bridged this gap. In our Journal of Microwave Power and Electromagnetic Energy paper, we officially distinguished between material and film. We proved that while material absorption is independent of thickness and monotonic, a thin film on a metal backing must be characterized by wave mechanics, the vector interference of reflections from the front and back interfaces. This led to our 2022 companion treatises, establishing the wave mechanics framework of microwave absorption. We bypassed their corrupt peer review cartel. We stood on first principles. Thank you for watching, and remember, do not bow to their consensus, stand firm on the absolute truth of mathematical reality,